Please let me know if you can see it. You can see it okay?
Great.
Great, and I will try to monitor the Q&A here, but if something needs to be addressed and I don't see it because I'm focused on the slides, please just let me know. So before I get into the content of the talk, I just want to thank Ray and Hongtu, Tony, Deeping, and Michael for organizing this. I think this is really cool. And so it's an honor to be here and to talk to everybody. I also want to acknowledge that the work I'm going to present is primarily the work of student Jack Zhu, who's now at Amazon. And so he did all the heavy lifting here that I will present. So yeah, okay, so without delaying further here, let's go ahead and get into it. So I'm going to talk about precision medicine. And this is now a maturing field. And so I think we all know the goals of precision medicine, but the thing that everybody likes to say is, the goal is to deliver the right treatment for the right patient at the right time, or the right, treatment for the right patient at the right dose at the right time, and so on. And this is based on this idea that's been around for well over a century, that in order to treat patients optimally, we need to tailor the treatment to their individual characteristics and situations. And that's what your clinician does every time that they assign a treatment or an intervention to you. And the idea being that if we can identify, if and when patients should receive treatment, then not only do patients do better, but also reduce cost and burden, resource consumption, and so on. But our goal here is to mathematize this or formalize this, and we do that using what I'll call a treatment regime. And so this is the formalization of sequential decision-making as a sequence of decision rules, where each decision rule is a map from the information you have at the time the decision is being made to a recommended clinical intervention. And so you can think about this as a recipe for how to adjust treatment over time to the evolving health status of each patient. And here, just for simplicity, I'm going to define an optimal regime as one that maximizes the mean of some cumulative clinical outcome if you were to apply it to the population of interest. There's other definitions of optimality. You could look at a quantile, for example. Ray has done some work on that, as have others. But for simplicity, we'll look at mean utility. Okay, so I first wanted to talk about kind of the state of the field for 2 slides, and then kind of just to give a little bit of perspective on where we're coming from. So the current sort of view, or at least a predominant view, is that we're going to take data and we're going to estimate a treatment regime, and then we're going to deploy it to make decisions in the population. So the idea is we estimate some kind of rule, and then that rule is used to assign treatments to patients. And if you take that perspective, then you really focus a lot on maximizing sort of the performance of the rule that you estimate. And so this has led to an emphasis on flexibility, say, rather than interpretability. And so there's been this huge surge of really innovative research in machine learning and semi-parametric and non-parametric methods. There's not enough space in the slide to go over them all, but I've listed some of the sort of early developments, things that are kind of analogs of large margin classifiers, flexible regression type methods, and then just to sort of highlight how much of a focus this has been in statistics. If you look at JASA, the flagship journal of the American Statistical Association, the theory and methods arm of the journal has discussion papers in 2016. There's 4 discussion papers in 2020. In the applications and case studies arms, there's 3 discussion papers, all about flexible estimation of treatment regimes. So this is getting a lot of attention in the statistics literature in terms of not only papers being published, but also just sort of attention and discussion. And so this is definitely a hot area in statistics. But when we look at impacting clinical research, and so I don't mean to discount any of this because I think this has really been innovative and advanced the field. But there's another perspective, which is how do we drive change in clinical practice? And here, we just need to recognize the reality that often, not always, but very often, the estimated regime is done as part of some kind of secondary analysis. So we are doing our primary analyses, which might be a simple comparison of say 2 treatments, and then we do some secondary exploratory analysis where we try to generate new hypotheses or ideas that can then be followed up in subsequent studies. And so when we take this perspective, the emphasis becomes on generating new clinically relevant information or emphasizing interpretability in a domain context rather than just raw performance. And so I have this kind of very simplified diagram of sort of the iterative collaborative process between data scientists and clinicians. So often we start with some kind of clinical hypothesis, we design a study, we run the study, collect data, we run all of our primary analyses. And then after we've done that, we do our secondary analyses, and part of which we estimate an optimal treatment regime. Then we look at the regime through the lens of a domain expert and try to see if there's any new insights to be gleaned there. And if so, then we posit new hypotheses, we run more studies and so on. And so this goes on. This is a long, slow, iterative process. And the idea is we want to drive change in clinical practice, but we need to do so in a way that is safe and in a way that is grounded in sound domain knowledge, right? So this is kind of the perspective at which this talk, this talk takes, or this work is sort of motivated by. And to give you a sense for why this is hard, here's the motivating study that I want to sort of focus on today. So this is a STEP BD. This was a study of bipolar depression disorder. It had both a randomized pathway and an observational one. So I'm going to focus on the observational pathway. And our goal here is to generate new knowledge about how we should be treating patients with bipolar disorder. And you can see from the picture that this is a complicated study. So on the x-axis here is time and days. We've lined everybody up from enrollment, so sort of everybody's aligned to the left. And each row here is a patient. So we selected a random set of 7 patients, and you can see along these horizontal lines, these pills here, these pictures of pills, these represent the treatment they received and at the dose. And so the key here, the legend is on the right-hand side. You can see the different drug types. And so if we look at this first patient in the first row, they started off with 3 different drugs, 2 at a medium dose, 1 at a high dose. And then they came back a few weeks later, stayed on the same dose. They came back a few days after that, and they removed one of the drugs and reduced the dose of another one. Then they came back a few days later. They further reduced the number of drugs from 2 now down to 1. A couple weeks later, they came back, they added a new drug, and so on. And so you see this change in treatments, not only in dose, but also in drug type. And so this is a case where they sort of scaled them down and then changed and scaled them back up. Here's one where they sort of ramped them up. They started them off on lithium, then they took them off lithium, put them on a new drug at medium dose, increased it to a large dose, added a supplemental drug, increased the dose of the supplemental drug, downgraded the dose, and so on. And so if you look at all the patients in this study, there's 1,300 or so patients, and you coarsen the time to weeks, no 2 patients have the same treatment history. Okay, so this is a very complicated sort of set of observational data, and if we want to extract information about how we should be treating patients, we need to find ways to incorporate structure from the science of the problem into the statistics of the problem. So what do we do with data like this? Well, first, we need to settle on what the goals are of the study. So just a reminder, it's a long-term study of bipolar disorder. It's an observational study. We saw from the picture, there were frequent treatment adjustments. The clinic visits were sparse and irregularly spaced. So if we go back here, some people were coming in very frequently. Others came in only a few times or 2 times. No 2 patients had the same treatment history, even after you coarsen the data to 2 weeks. And the scientific objective here is to identify how patients are and should be treated to manage bipolar symptoms. So there's kind of 2 questions here. If we look at this, you could ask, why and how are clinicians making the decisions they're making? So what's driving these treatment changes? And the second thing, and the thing I'm going to focus on today, is how should we be making those treatment adjustments? What drug should we be selecting and at what dose? Just to give an example of what that might look like, here's an estimated optimal treatment regime using that data. And I'm going to talk about how we constructed this in the remainder of the talk. It says if you're at a high risk of a depressive state, so these are bipolar disorders, so they might oscillate between mania and depression. So if you have a high risk of a depressive state, and if your depression score, some D, is high, and your mania score, some M, is low, then give a low dose antidepressant and a medium dose antidepressant and a low dose mood stabilizer. Otherwise, give a medium dose mood stabilizer, and so on. Okay, the point of this rule is that we can look at it and we can evaluate it from a clinical perspective. And if you study this long enough, what you'll see is that it's suggesting that you should only get a antidepressant if your risk of transitioning into a manic state is low. And I'm not going to get into the science of bipolar depression, but that is a reasonable hypothesis in this domain. And so looking at a rule like this and then extracting that kind of personalized treatment recommendation, don't give an antidepressant if the risk of transitioning into a manic state is high, is the kind of thing we're trying to do here. So can we get hypotheses like that that are clinically meaningful, that can drive change in clinical practice? Okay, so how do we make progress in a problem like this? Because we have time varying confounding, meaning the treatment decisions now affect the subsequent patient state, which in turn affect the treatment decisions in future. We have sparse and irregular clinic visit times. We observe data over a finite horizon, but our goal is to inform treatment over an indefinite horizon. So we obviously only have data over the length that the study was run, but we want to estimate a rule that we can apply as long as the patients need care, which could be their entire lives for a lot of these patients. There's a lot of treatment changes and dose changes, and so we can't pool patients by treatment history. As I mentioned, there would be one patient per group if we did that. And so what that means is you can't naively apply something like inverse probability weighting, which has indicators for each possible treatment history. And Q-learning is unstable unless you have additional structure, which I'm going to talk about next. Okay, so what's the idea here? The idea is to take some of the scientific theory and bring it to bear on the problem. And so one of the things we're going to use here is this model of bipolar depression. So the idea is, and I'll talk about the picture first, that patients are transitioning among a small number of states. So they could be recovered, they could become hypomanic, they could become manic, they could be a mixed state, they could be depressed, and so on. And you see that this is not fully connected. So there is some structure in the links, but then also just the idea that if we knew which state they were in, that would give us a lot of valuable information about how best to treat them. And if we knew how likely it was that they were going to transition from one state to the next, given what we can observe about them and given the candidate treatments, that would also be extremely valuable in terms of deciding what's the best treatment for each patient. So we're going to assume that patients are transitioning among latent health states as depicted here. Given a health state, we're going to assume the process is Markov. So the idea is we don't assume the observed data are Markov. That's not reasonable given what we know about the science. But given what we do observe and this latent health state, then we can assume, then we're going to assume that it's Markov, and that is aligned with the current theory for this disease. And then it will just be a matter of deriving estimating equations for the optimal treatment strategy by adapting known methods for Markov decision processes, which are ubiquitous in reinforcement learning. Okay, so this is for those who are working in ARL will recognize this is a POMDP. Or actually it's a slightly more general thing. It's a partially observable semi-Markov decision process, and there's an enormous literature in CS on POMDPs and especially focusing on the Markov case, but there's some work in the semi-Markov case too. So what's different about what we're doing here is our focus is really on data efficiency. So how do we use the data efficiently to do things like inference? How do we construct confidence intervals for the performance of an estimated rule? How do we do tests for coefficients to see which factors are important in deciding treatment and so on? And also, how do we integrate clinical theory in a meaningful way into these models? So this is really addressing a clinical need and a statistical need more so than addressing a gap in the CS literature where the focus has been on, I would say, performance, and maybe generalization error bounds and so on. But I think our focus here is distinguished by this kind of focus on stat inference and driving clinical decision making. Of course, there's another view of this. If you want to take a purely methodological view, you can just think about this as a general purpose and a pretty straightforward way of taking non-Markov data and making it approximately Markov by assuming there's some latent structure that is a good way to summarize the history so that you can then apply all the existing kind of MDP tools that we have. And it's in some ways preferable to purely data-driven approaches because you're using this clinical theory. So and I won't show these simulation experiments here, but it does do better than just something like sufficient dimension reduction or PCA or auto-encoding and so on. These can be difficult to apply in our setting because unless you oppose that additional structure. So we tend to focus more on the sort of clinical perspective here, but there is this sort of alternative view of just how do we take non-Markov data and make it approximately Markov. Okay, so in the remainder of the talk, I'm going to set up the notation and state the problem formally. Then I'll go through some estimating equations for the optimal treatment regime and state a couple of consistency and asymptotic normality results. And then we'll look at simulation experiments and close with the discussion. So first, what's the setup? So we assume that we observe n IID copies of a trajectory that looks like TAX. And so here, each patient has J clinic visits. So J is random, right? So each patient has a potentially different number of clinic visits. Those clinic visits occur at times T1, T2, and so on up to TJ. We rescale time, so it's between 0 and 1 just for convenience. AJ is a treatment which is assigned at time TJ. It takes values in a set 1 through L. And this is a treatment that's applied during the period TJ to TJ plus 1. Right, so that's the treatment the patient receives during that window. XJ is the patient measurements that are taken at the clinic visit at time TJ, and we'll assume that takes values in RP. And as I mentioned, both the number and timing of visits are treated as random variables. Okay, so to make the notation more compact, we'll define the history H1 to be T1 and X1, and HJ to be the previous history, new treatment decision, new time point, and new covariates. So HJ is the information you have at time J, or at visit J rather, to make a decision for that patient. Okay, so the goal is to estimate an optimal regime that we can apply over an indefinite horizon, meaning that we can apply it over a longer horizon than the data were collected. And so what that means is we're going to need something that is stationary, or at least can extrapolate beyond the window over which we observe patients. And so this will be formalized as a sequence of functions that map patient history to recommended treatment and maximize some cumulative measure of health. And the way we're going to set this up is as follows. So regime pi is just a sequence of functions pi j for j greater than or equal to 1, where pi j maps a history to a treatment. So a patient who presents with history hj equals little hj at visit j would be given treatment, recommended treatment pi j of hj. But in the interest of assigning rules that can be applied indefinitely, and also match this idea that the time scale should really be irrelevant, given if you have all the sort of relevant patient features, we're going to consider regimes that look like this. Pi is the composition of some stationary function rho with some sequence of functions f, so that pi j is rho composed of fj, and fj is a sequence of summary functions. So fj takes as input a history and it gives back a summary of that history. And that summary takes values in some fixed set script s. So we'll define sj to be fj of hj, so that's a summary of the history. And then once we have that summary, we apply our static rule rho. And so the reason this is useful is that if we can make fj somehow qualitatively meaningful, so suppose it was just a running average, so we look back over some number of time points in the past and average the patient features, or it's some kind of estimate of a slope of, let's say, a depression score, something that is clinically meaningful. And then we look at the rule rho, which is essentially being applied to the same information at every time point. Then we can evaluate this from a clinical perspective. Does it make sense, for example? Oh, I thought there was a question. All right, so I just want to show a picture of what this looks like, because I think this will help drive the point home. So here's the raw data. You have X1, those are baseline patient measurements, A1, which is the initial treatment, X2, which are subsequent measurements at the second clinic visit, and so on. And the history at time 1 is just X1. The history at time 2 would be X1, A1, and X2. So that's the information you have before assigning A2. And H3 would be X1, A1, X2, A2, X3 before you assign A3, and so on. So the history is growing in dimension, right? So once we sort of reach the final observation point in the study, we can't extrapolate further because we won't have any histories sort of that size at time t plus 1, let's say, or j plus 1. So what we want is we want to construct these functions f, f1, f2, and so on that take a history and map it to what I'll call a state S1. So H1 gets mapped to a state S1, F2 maps H2 to another state S2, and so on. And the idea is that these states all live in the same space. And then you have a new process where S1 is the information that you use to choose A1, which then drives the observation of S2 and so on. And we want to operate on this space down here because this is going to be, if we construct these Fs correctly, approximately Markov and homogeneous. And so we can apply a static decision rule that can be applied indefinitely, no matter how far into the future we go, even if it's far beyond the duration of the study. Right? So the idea is going to be, well, how do we construct these Fs so that this process down here is approximately Markov and homogeneous? And if we construct an optimal treatment assignment rule for this process at the bottom, it is optimal for the original process. So that's the idea. And to do that, we're going to assume that we've constructed these states S so that the utility function, say the utility at uj is a function u of sj aj, so it depends only on the history through sj. This is not really an assumption about the generative model. It's an assumption that we've just made sure to capture whatever was important for defining utility in S. So we have to make sure that however we define utility has to be part of S. So that's just really a definition. And so we're going to try to maximize the sum of these UJs, the sum of the utilities over time. And we're going to focus on two ways of accumulating these utilities. One is discounted. So we'll define V, so discount of a regime pi or policy pi to be the expectation if you assign treatments under pi of the sum from j greater than or equal to 1 of gamma to the j minus 1 to the uj. So this is the discounted utility. So this thing gamma is discounting future. So it's telling you, how much should you discount future utility in sort of today's terms. So those who work in finance will be familiar with this kind of discounting. Here it's a bit more of a ad hoc rule. I mean, sometimes you can talk about what's the probability that the patient dies and try to define gamma that way, but in general, it's more of a tuning parameter. Another approach is to look at the average reward, so VAV. So here what you do is you take the limit as n goes to infinity, the expectation of 1 over n times the sum of the utilities from j equals 1 to n. And so here, you're just looking at long-term average performance of the utility, whereas in discounted, you're sort of upweighting near-term utility relative to future utility. And an optimal regime in terms of either criteria maximizes these V functions, these value functions. So pi opt will maximize give you the largest value of V relative to any other pi. And so I will sometimes put these little black dots in place of either DIS or AVE to indicate that we're referring generically to either one of these two criteria. Okay. All right, so our goal is to construct an estimator of pi opt. Okay. So now, how do we first characterize the optimal regime so that we can construct an estimator? Well, we can't identify pi opt from the observed data with a finite horizon. So if we don't put any more structure in the problem, there's no way for us to identify pi opt. And the reason, of course, is that we don't have data beyond the length of the study. So if the system were, say, non-Markov and non-homogeneous, then there's no hope, right? There's absolutely no hope because you don't have data beyond the length of the study. So you can't say anything about what the optimal treatment is out there. So in order to make progress, we're going to impose structure that's informed by the underlying clinical science. And in particular, we're going to try to construct those summary functions F so that the process Sj, Aj is Markov and homogeneous. And once we do that, then we can apply batch off-policy reinforcement learning methods, which have been studied extensively. So there'll be some amount of work to do in terms of getting the inference, but otherwise we can more or less apply off-the-shelf type methods. So the real challenge is how do we construct these summary functions Fj? So how do we summarize the history into some common space? And for those who work in PalmDPs, you can guess the answer. It's to look at the belief state. So assume that there exists some latent Markov process MT, which transitions among k latent states, which I'll label 1 through k, so that xj plus 1, the observations at time j plus 1, are independent of the past history and treatment, given the current state, the current observable is xj, the treatment, and this latent state, which you don't observe. So if this structure holds, then we're going to be able to construct a concise summary. So for example, this latent state might encode these states like depression, recovery, mania, hypomania in bipolar disorder, but you can generalize it to more to larger spaces or even continuous spaces. But if you have this structure, Then we have the following results. So let Bj denote the conditional distribution of the latent state given the history, and define Sj, which again, remember, is our function of Hj, to be this conditional distribution and the observed state at time j, and we'll define their domain to be script s. And if the utility depends on the history only through the state s, which includes current observations, which should include utility and this distribution, and the current treatment, then Sj, Aj is in fact a homogeneous Markov decision process. And if you maximize over static rules that just map state to actions, that's the same as maximizing over the entire space of possible regimes. So essentially, if you can get the conditional distributions of the latent state and concatenate it with the observables, then you can just treat this as an MDP, solve the MDP, and it's equivalent to solving the original problem. So this is, I mean, a variation of a well-known result in PalmDPs. So one thing that, sort of in plain English here, the current observation plus the conditional distribution for the latent state together are sufficient for identifying the optimal treatment regime. But a natural question is, if we define something to be sufficient, is it minimally sufficient? And it turns out that it is, in the sense that this is sufficient, and you can show that there exist generative models such that further reducing the state, meaning if you try to get something smaller than this, you will no longer be able to identify the optimal regime. And so there exist generative models for which further reduction of the state, say if you take some function Rj, which is a function of S, so that the conditional covariance of Sj given this reduction, so you can't recover Sj from R. So if there is some variance left, then with probability 1, you get a lower value. So the point here is that there exist generative models where you cannot reduce it further. So it's minimal sufficient in that sense. There are generative models where you could reduce it further, but there exists some where you cannot. So in general, it can't be reduced further. So again, to just sort of restate this in plain language, under some generative models, Sj is necessary to identify the optimal regime. So in that sense, it's minimally sufficient. Okay, so now it's just a matter of kind of going through the exercise of estimating this distribution and then plugging in and then showing that you can propagate the estimation error into statistical inference. So to do that, we're going to look at estimating equations for the optimal treatment regime. And we're going to focus on two well-known, or I maybe shouldn't say well-known, but at least they've been used in clinical practice for Markov decision processes. And so the idea is that they've had some clinical traction already. There are other estimating equations that could be used. So first, we're just going to review the optimal, how to estimate the optimal treatment regime for the average reward setting if you had an MDP. So we don't have an MDP, and we're going to estimate the state from the data. But first, let's just review what we would do if we did have an MDP, so it'll be clear how the plug-in estimator works. So suppose you have data that comprises NID trajectories, Sj, Aj, Uj. So Sj is the state of the Markov decision process, Aj is the action, and Uj is the utility. Then for any regime that maps S to A, states to actions, we can define the differential value delta pi S to be the limit as n goes to infinity of the expectation under pi of the sum from j equals 1 to n of the utility minus the average value of pi given S equals little s. And so this term here has you can sort of look at it as a bias term. And the critical thing here is that there's this expectation so that this is finite and well-defined under mild conditions. So this is sort of how the average reward ends up sort of converting to VAV given that you're starting in state S. So it sort of captures the bias induced starting from state S. Because eventually, if the process is mixing, it won't matter where you started in terms of the average value, right? But in the short term, it will matter. So that's what's happening here. And so that's the average value. And then you can show just from some simple algebra manipulating this equation and the equation for the average value that for all j and for any function psi that maps states to Euclidean space, the average value and the differential value satisfy this estimating equation. So 0 equals the expectation I see there's a question, I'll answer it in a second, of the indicator that treatment is consistent with pi divided by the probability of treatment AJ given the state, so the propensity score, times the utility minus the average value plus the differential value at the next state minus the differential value at the current state times psi. So here we have this estimating equation, and what's critical here is that this expectation doesn't have a pi on it. This is expectation with respect to the data generating model, which means that we can use it to construct an estimating equation for both VAV, which is what we care about, and then this is a nuisance parameter. So there's a question here, which is how to characterize the distribution of the states. Is the initial state different for each patient? Yes, the initial state is different from each patient. They're assumed to be drawn from some distribution. And so we'll talk about that in just a few slides. Good. Okay. So once we have this, then it's just a matter of replacing this expectation with respect to an average over the data, which is what I'll show you here. So you posit some kind of parametric model for the differential value. I wanted to say that this comes from Murphy et al. And Luckett et al. If you want to get into the details of the estimating equation. So I'm not going to go into the derivations, but if you want to see those, that's exactly what this is based on. So you posit parametric models, say delta pi of S beta, indexed by some parameters beta. And here we're focusing on parametric models. Actually, there's work with non-parametric models also. And then we're going to set psi, our function psi, which was here, to be 1. That's going to be corresponding to the term for the average value, and then the gradient of this model with respect to beta, and define v hat of pi and beta hat as solutions to this equation. So what's happening here is I've just replaced the average with the average over the data. We've summed over the time points, and then we've just replaced these parametric models for the differential value. And so you solve this thing for VAV and for beta hat. And then for any class regimes capital pi, the estimated optimal regime is the one that maximizes V hat av pi. So you can imagine conceptually sort of alternating between positing a pi, solving this estimating equation to get V hat av of pi, and then climbing uphill in the space of policies. And there are, of course, more clever ways of doing this computationally, but that's conceptually what's happening. So in step BD, we consider classes pi that are representable as trees. But of course, you could use any class that was appropriate. Okay. One other thing I'll note is that it's possible to derive more efficient weighting functions here. But the optimal weights depend on the unknown system dynamics. And so I'm not going to talk much about that, but although we have worked that out, that does exist. Okay. I'm not going to talk about the average reward case in the interest of time, but the derivation is similar. Okay, so now what do we do? Well, so that we derive these estimating equations assuming we observe the state, which we don't. So what we do instead is we take the observed data, which is here. This is the raw data that we observe, time, action, and patient measurements. And then we estimate the latent state. So we get S hat J and actions which are observed. And then once we have this, then we can apply the method with S hat replacing S in those estimating equations. And so in terms of the high level overview of our assumptions in the application, we posit models for the latent process dynamics. So for example, a Gaussian autoregressive model. The clinic visits, we assume that they are independent of the latent process. So that's important. So that the visit times and the times between visits are independent of the latent process. The transition kernel is stationary and recurrent and aperiodic. We also assume just sort of standard regularity conditions, meaning the moments that we need exist and so on. And under these assumptions, you can apply standard hidden Markov model theory to establish the asymptotic behavior of S hat. So basically, you estimate S hat using maximum likelihood, where you've posited a model for the latent process. Okay, and then once you do that, then you can apply this estimating equation with S hat in place of S. And just to give a little bit more detail about the kind of things you have to posit here. So you need a model, and this gets at the question that was in the chat. We have a model for the distribution of the initial state given, or the initial observable given the latent state at time 1 that's indexed by some parameter, say theta. And then we also need a model for the distribution of the next state given, or the next observable given the latent state and the previous observable, which we assume again is some parametric model indexed by eta. And then if we define rho to be both parameters theta and eta, then under the positive model, there exists some function, I'll say little bj, that maps the domain of the history to vectors of length L, where L is the number of latent states, so that the estimated distribution of the latent state given the history and these parameters that the probability distribution is a deterministic function of the history and these parameter vectors rho, which you don't know. So the point here is that if you knew that these parameters eta and theta, then you'd be in business because you could construct the distribution of the latent state given the history. It would just be this deterministic function of those parameters. It's a complicated function, but it's a deterministic function. And so the idea is just to construct an estimator rho hat of rho star using maximum likelihood. And then the plug-in estimator of the latent state is S hat j, would be bj, this function here, of the history, and then rho hat, comma, xj, and xj is observed. So this is how you construct an estimator of the latent state. So it's just a matter of doing maximum likelihood and then plugging in, basically. Okay. So then once you do that, we also have to plug in the state into the utility function. So u hat is now the utility function applied to s hat rather than just s, because we don't know s. And then for any pi, we can solve for beta hat and the average value by solving these estimating equations the same as we had before, only now we have s hats in place of s. So wherever there was an s, we have an s hat. Wherever there was a u, we have a u hat for the estimated utility. Of course, if the utility depends only on x and a, then you don't have to estimate it. But if it depends on other latent factors, like the probability of transitioning into a depressive state or a manic state, then it'll have to be estimated. And then we solve this estimating equation for v hat av for every pi, and we take pi hat to be the maximizer over the average value. Okay, so this is, from an algorithmic point of view, this is pretty straightforward. You just do maximum likelihood and then solve an estimating equation and maximize. The question is, does the statistical theory still go through? So this is the applied reinforcement learning seminar series, and so I don't want to get bogged down in a lot of theory, but I just thought I would give a high-level overview of what kind of assumptions we made that were relevant to the application, and then also make the theory go through. So we assume a linear model for the differential value. It was some basis expansion. We have a feature diversity condition. So for those who are familiar with like sequential regression or bandit problems, it's basically this eigenvalue condition to ensure that you're accumulating information over time. Weak differentiability of the utility and the latent state distribution. There's another question I'll get to in just a second. The class of pi has finite VC dimension. And so if we look at trees of fixed length, for example, and then moment conditions. And so under these conditions, and of course, we make implicitly the causal conditions needed to identify the causal, like the known measure confounding and so on. Then you can show that root n v hat av of pi minus v av converges weakly to a Gaussian process indexed by the policies pi. So here, bold B of pi is a Brownian bridge indexed by pi. And why this is useful is that you can then use it to construct confidence intervals for the optimal, the value of the optimal policy. So V av pi opt, for example, when we talk about that in the paper. So one of the questions was, what is the purpose of rho? Is it for decreasing the sample space? No, the purpose of rho is to model the interplay to link the latent distribution and the things you're observing. So we don't observe the latent state, and we assume that there's this latent structure, and so we need some way to link the observed data with this latent process, and the way that we do that is through these models here. And then rho is just the concatenation of the parameters indexing these models. Thanks. Okay, so from this, we can derive inference procedures, testing procedures, and so on. Okay, so just a quick summary of the approach at a high level. We don't assume the process is Markov, but we do assume there exists some latent health process. So the conditional on that process then we have, then the process becomes Markov. We transform the data so it approximately follows an MDP, which then allows you to apply your favorite methods. And then you can do that to construct an estimator of the optimal treatment regime as if you were in the MDP setting. And then you can apply methods from empirical processes and so on to do inference, where you just have to propagate the uncertainty of the state through all of your arguments. So we focused on one set of estimating equations here that were based on the work of Murphy and Luckett, but there's lots of other approaches that could be used. We just chose these ones because, as I had said previously, they've been used in clinical practice before, and so there's some buy-in from the clinical community with those models, and they're highly extensible and flexible. Okay, so let's just have a look at some simulation experiments. So we're going to simulate data to try to mimic the important features of step ED, and so here we're looking at in the simulation experiment, we'll look at 3 treatment options that are assigned. So that the conditional distribution given the history is a multinomial logistic regression. So the idea here is that treatment decisions are based on past history to reflect the fact that this is an observational study in which clinicians are choosing treatment based on the evolving health status of each patient. We'll put 5 latent health states. This is to encode, this idea of depression and mixed and recovered, hypomanic and manic. And the interarrival times in that latent process are an autoregressive exponential generalized linear model that has a random intercept, so a different intercept for each patient. The observations are 3 dimensions, so xj is an R3. And given the latent unobserved state, the previous observation and treatment, we assume that this follows a Gaussian autoregressive model. And the utility uj is 2 minus the first absolute value of the first component of x minus the absolute value of the third component of x. And this is to mimic this idea of like balancing depression and mania. So you can think about x1 as being like a deviation score where being 0 is good and being far away from 0 is bad. Same thing for x3. So one might be, say, depression, the other one might be mania. And so we want to try to balance the two. So that's the idea. And we'll look at both correctly and incorrectly specified models for the latent process. We implemented the estimating equations with the latent structure and without the latent structure. So one natural question is well, what if we just ignored this latent structure? What if we just pretended it was an MDP and sort of forged ahead? How much would we really lose if we did that? Maybe it's robust to that lack of Markovian structure, and everything will work out. So that was a natural question to ask, we thought. We'll look at a linear model for differential value, one that has main effects only, which I'll call linear, and pairwise interactions in quadratic terms, which we'll label as quad. Pi is, in this case, is a set of linear decision rules, and the performance is based on the average value. So if you look at this, there's kind of 2 expectations here. One is an average over future patients given pi hat, which you've constructed from the data, and the outer expectation is over data sets. So it's the average performance of a rule estimated using these different methods. Okay, so here are the results. So the columns are as follows. The first column is sample size. The second one is the value of the treatments, the performance of the treatments as they're assigned by clinicians. So just the value of the treatments being assigned in the generative model. The value of using a linear MDP. So here, the idea is that you ignore the latent structure and just pretend it's an MDP. Same thing with a quadratic model. Then we have the linear model where we assume the latent state, a latent structure, and a quadratic model where we assume the latent structure, and then the optimal value. And the first portion of the table is that the model is correctly specified. The other one's where it's misspecified. And we tried to pretty severely misspecify the model to give a rigorous test of robustness here. So in the correctly specified case, the observed value was about -0.5, -4.8, or sorry, 0.48. And the linear MDP in this case is actually worse, -0.95. And so it really is getting a lot wrong here in terms of the treatment recommendation. So it's worse than what clinicians were doing. Same thing for the quadratic model for the MDP. Whereas if you use the latent structure, the value is basically about 0. And so it's significantly better than the value as it was assigned, and it's very close to the optimal value, which is 0.063 and 0.071 here. These are really the same value. We had to estimate these with Monte Carlo, so that's why they're different. They're the same. Okay. And now we look at the misspecified model. So here, V obs about minus 0.3. The linear MDP did okay. Now it got to a value of about 0.02. Same for the quadratic MDP. No real difference here. And then if we use the latent structure, we do significantly better. So even though it was misspecified, 0.26 and 0.27 for the linear model, 0.26 and 0.27 for the quadratic model. So there really wasn't much of a difference when including those quadratic terms. And V opt was 0.4. So we made up about half the distance between the MDP model and the optimal model by using this latent structure, even when it was misspecified. So in terms of constructing a confidence interval, so in the paper we talk about how to construct an asymptotic confidence interval for V-av of the optimal rule. So it turns out that this is a non-regular problem, so additional kind of adjustments have to be made. But the key argument is that distributional, or the convergence result of V hat of pi that we showed. And so when the model is correctly specified, the coverage is 96 and 97. So the target was 95. So we're a little bit conservative. And that has to do with the adjustment we made for non-regularity, which I didn't really talk about, but it's in the paper. And in the misspecified case, we were a bit more conservative, which is to be expected. We tried to err on the side of being conservative under misspecification or non-regularity. So here, this is promising because constructing confidence intervals for the average value of the optimal rule is known to be a difficult problem. So finally, just to return to the motivating application, if we look at step BD, so we have, in terms of patient covariance, we have depression score, mania score, bipolar type, and so on. I'm getting some kind of feedback. I don't know if people can mute their microphones if they're not talking. I'm just worried other people are getting that same feedback. Okay. So in terms of the model, we look at, there was some item missingness, and so we're looking at multiple imputation. It was very little, but for the item missingness, we use multiple imputation. We use a Gaussian autoregressive model for the evolution of the observables, xj, a semi-Markov model for the latent health process, and an AR exponential generalized linear model for interarrival times. The utility here is 2 minus some m, that's the mania score, minus the depression score, where some m and some d, the mania and depression scores, have been normalized to lie in 0, 1, with the idea that a score of 0 means no symptoms and 1 means the most severe symptoms. And so again, we impose this structure on the latent model, as we saw at the beginning of the talk. And if we impose this structure and estimate the model, again, just a reminder of the data and how messy they are, the one challenge is like, how do we deal with all the different dose combinations? And so with our clinical collaborator, we reduced the sort of complete number of treatment options to 15. And these 15 treatment options range from low dose antidepressant, low A, up to high dose antidepressant and and high dose mood stabilizer. And the reason we did this was that there are several drugs here that are in the same class. And so it would be more meaningful to recommend, say, low dose antidepressant and low dose mood stabilizer than the specific drug. So it's giving them the dose and the type, and then the selection from the specific drug, say whether they go with a name brand or generic or similar, is left up to the clinician. Because that may depend on other factors that are not really relevant clinically, but maybe have to do with cost or local availability. Okay, so there are 15 unique treatment possibilities here. And when we take these 15 and we estimate a rule, here's the rule that we get out. And so here we represent it as a decision tree. And so, for example, you can see that if some D is greater than 1, so if the depression score is equal to 1, they have most severe symptoms, and their bipolar depression type is 1, then they get this red treatment, which is treatment number 11 on our list here, which is medium dose antidepressant and medium dose mood stabilizer. And you see that of the 15 treatments, there's really only 3 unique treatments that appear in this tree. And those are low dose mood stabilizer, medium dose mood stabilizer, and then medium dose antidepressant and medium dose mood stabilizer. And if you stare at this long enough, you realize that this too is saying that you should only give the antidepressant if the risk of transitioning into a manic state is low, rather, because you do not want to give somebody an antidepressant and then have them swing from depressed to manic, And so that's really a clinical concern. And so this is aligned with that clinical thinking. And so clinicians can look at this rule and generate hypotheses of that form and then go and follow them up with subsequent studies. So in terms of the observed value, so if we just average patient outcomes, observe average utility of 1.6, whereas the value under the estimated optimal regime with a 95% confidence interval goes from 1.72 to 1.88. So it seems to give you a significant improvement. And the nice thing about the average utility is it's in the original units. So you can talk about a gain of 0.2. This is on in terms of the scale, and it turns out that's a clinically meaningful difference. The discounted utility is harder. Here we use a discount factor of 0.95. The observed value is 14.4. The value of the estimated optimal rule and a 95% confidence interval goes from 19 to 46, the point estimate of 33. So again, it's significantly better, but it is harder to talk about these units in a way that's clinically meaningful because they're discounted and cumulative. So the average utility is in some ways easier to think about clinically. Okay, one other neat thing about this study is they gave a detailed inventory to try to assess their status. So in general, we wouldn't know what the clinical status is of these patients, but because they did this additional inventory, we can compare our latent state probabilities to what the clinician thought was the actual true latent state. So this gives us a way to test the validity of the latent model, which wouldn't normally be possible. And so here we have, going across the rows, the status that the clinician thought the patient was in based on this extensive inventory. And then in the columns, we have the estimated probability the patient was in those states. And so what you see is if we look at depression, we have agreement of 85%. If we look at mixed, it's 84%. If we look at stable, it's 92%. But if you look at mania and hypomania, you see that the agreement's only about 50% or 44%. And the reason is that hypomania and mania are just different degrees of the same thing. And so there's lots of clinical disagreement about whether you are manic or hypomanic. And so the confusion between those two states that we see in our model is expected and also may reflect just a lack of internal consistency in terms of the clinician's ratings. And so we thought this was really promising in terms of seeing this latent state model that in some ways be validated anyway. And so this sort of shows the connection between the model that's used here and the clinical theory. Okay, so just to wrap things up, so we proposed a methodology for estimating optimal treatment regime when you have complex observational longitudinal data. We showed you could leverage a lot of these ideas from partially observable semi-Markov decision processes. We extended those methods to allow for inference, especially for the estimated or for the optimal decision rule or the optimal treatment regime. We didn't assume the data were Markov. It allows for sparse, regularly spaced treatment changes and the presence of many treatment options. The critical thing here was to use clinical theory to make the problem more tractable. But there's, I think, a lot of open and interesting problems left to think about, and I'd be happy to talk more about those with those who are interested. And so maybe I'll just stop here and give a shameless plug for our book. If you're interested in dynamic treatment regimes, this just came out a few months ago. And so thank you. I'll stop there.
Thank you, Eric. This is very interesting. Maybe you can go to the chat window to answer some questions. I think someone posed a question on the chat window about, can you explain the purpose of the role? I guess you need to go back to your slides.
That row. Oh, yeah, I see. Okay. Yep. So let me go back. Good question. I think they maybe asked that before and I misunderstood. So let me go. I think this was asked before and I might have misunderstood the question. So apologies if that would happen. I had a row and a var row, which is a terrible idea because I called them both row. Okay. So let's look at maybe I'll start by looking at this picture. So the idea is that in this setting, the data aren't Markov. And so you have this history that's accumulating to make decisions. So the available information at time 1 is H1, but at time 2, it's H2, which would be X1, A1, X2, and so on. And so you want to estimate a rule that has sort of two goals. One, it can be applied indefinitely. So for patients, as long as they need treatment. And it's clinically meaningful in the sense that it doesn't depend on time. So a rule that depends on time here This study is not from onset of the disease, right? It's enrollment in the study. So what you really want to do is you just want to look at their health status or some summary of their health status and make a decision based on that. It shouldn't matter, whether it's time point 38 or time point 39 necessarily in this context. And so what we want is we want rules that make sense in a holistic way, where the clinician can look at it and say, yeah, okay, this is the right way we should to treat patients, or this is interesting, and we should think about whether this is a valid way to treat patients. And so if we look at this rule here, let's see, I give a rule somewhere, right here. So if you look at this rule, notice there's nothing in here about T. It just says, if you are currently at a high risk of being in a depressive state. It doesn't say if it's time point 27 or if it's time point 42, right? If it's your 42nd, clinical visit, it doesn't say that because the clinical theory suggests that it shouldn't depend that way. There are diseases where that does make sense, but in these kinds of in this disease, it doesn't really. They want to say, given your health status, what should I do? So if you're currently in a risk of a depressive state, if your current SUM-D is high, if your current SUM-M is low, then do something, right? And so we want to estimate rules like this, where you can look at it and say, does this make sense? So if a patient presents with this health state, what should we do? Okay, so how do we construct rules like that when we know we don't have Markov data? So the idea was to go back to this picture. How do we take the history and then summarize it into something that is qualitatively similar over time? So how do we summarize the history? So in that rule I just showed you, what it's doing is it's taking their current health status. So it's looking at their current risk of transitioning into one of these states, manic or depressive, and it's looking at their current depression and mania score. So that's what S is as a summary of H. So notice it's not just X3, it's not just X. So if we look at H3 and we think about what's an X3, H3 has X3, A2, X2, A1, and X1. But H3 in this example would say, what's your probability of being in one of those states or transitioning in one of those states? And that depends on the whole history. But it's a summary that is meaningful now and it's not indexed by 3, but it's estimated from all this previous data, right? Because of that latent process, the probability of your latent state depends on the entire history. So it's a summary that's qualitatively similar over time. And so the purpose of looking at rho is to have a rule that doesn't depend on time, but to have that dovetails with these summary functions that make the state sort of the same over time. Does that help, Jaja?
I think it's very helpful.
Okay, awesome. Okay, so there's what factors contribute to the discount utility, gamma, and what is a common approach to find gamma? This is like this is a major open question. So how do you choose this gamma? So if you're in a business setting, it could be easy. You could say, well, okay, $1 next year is worth 90 cents, or sorry, yeah, $1 next year is worth 90 cents today. Then gamma is 0.9, right? That's an easy case. Or if you're treating subjects and they're going along and then they die with some probability and you want to model it that way. But otherwise, it's very difficult to choose gamma in a meaning. I think, at least, I shouldn't speak for as if it's this is completely agreed upon. But from my view, it's very hard to choose gamma in a way that's scientifically meaningful in a lot of contexts. And so it ends up becoming a tuning parameter because there is a trade-off. The smaller gamma is, the easier the estimation problem is, because you're extrapolating less far in the future. Or at least you're putting less weight on the future. So you can imagine treating gamma, and people have done this, as something you tune to trade off bias and variance. So maybe you care about long-term performance, but you also know that the farther out you look and try to estimate, the more variance is going to be in your estimator, and so you tune it that way. So it's not an easy problem. Sometimes people will just look at kind of how much weight is given at each decision point, and they'll say pick 0.95 or 0.9 based on how much weight it's giving the decision next week and the week after and the week after and so on. So I don't know that there's a good I don't know that there's a good answer for that this university accepted. Okay, so we have is the time interval the same? No. The time intervals are, these are clinic visits. So this is let me pull this picture up here. Good question. So these intervals are irregularly spaced, which is why we have a semi-Markov model for the latent state. So and also we let the arrival time be random. So these are random variables. So they're not equally spaced. So the visit time and the time between visits are treated as random. The data, and the next question in the queue is the data set public? Yes, it's publicly available. You have to request it from the National Institutes of Health. So you go to NIMH and you can request the data and you can get it. But so it's public in that sense, but you have to submit a request. So we can't post it online, but you can request it from them. Okay, next question in the queue is the motivating example, why the final results don't include all the treatment combinations? Oh, because they didn't appear to be optimal. So if you look at the argmax, that the set of the treatments that actually, maybe I can just go here. The set of optimal treatments is much lower than the total number of treatment combinations, which isn't too surprising. We think that giving high dose antidepressants is probably not going to be very safe for a lot of these patients because it's going to swing them into a manic state. So there's some clinical reasons, but also just the argmax set did not include all the different treatments. So they're all allowed, they're all considered in the optimization, but the set of optimizers is smaller. Yeah. Let's see. Oops. The next one, are the inter-arrival times the same? Nope, they are random. And is this, so this is a regular time series. This is a, yeah, I would say that that the time series data are regular, or it's irregular longitudinal data. Okay, so now we have one with symbols in it, so I got to squint. We posit models for the latent process given the previous latent state and the observable latent state given the previous latent state. With both of these models and the sequences are unknown. Any challenges in MLE for this part? And hat M is a distribution. So I guess the simplicity in our setting comes from, okay, so there's a few things here. So is it a difficult problem to estimate? So there's been a lot of work in this area that we're able to use. And I think that these algorithms have been optimized, and so especially for like exponential families is what we were using. So I think it is a hard problem. Jack would probably tell you that it was a difficult problem to get working computationally, but conceptually there are methods you can bring to bear here. So in that part, it's not so challenging, I guess. And then others have done a lot of the work there. Is there simplicity in our setting that comes from the fact that MT is discrete? I think one of the interesting things is if you make it continuous, then that thing that we called B, which was just a vector of probabilities, now becomes a distribution, and then you can use functional regression methods with your estimating equation. So we have some work on that, where if the latent state is continuous, then now the latent process is continuous, then the state now has two components, the observable X and then a distribution. So now you use functional methods, and so it makes it kind of interesting. So yes, we did get some benefit here, but you can do it the other way too. Next question, is there an assumption about the informativeness of the random visit times? Does the time between treatment decisions give information about the patient's status? Okay, great question. So the arrival times can depend on, or the transition times of the latent process can depend on treatment and on health status, and so can the visit times. But you need to make sure that you have what am I saying? You can model the inter-arrival times as functions of the health status and even the latent health status. So you can have models for those, but you need to make sure that the parameters are identifiable. So you couldn't have them be like periodic, for example, right? You need to ensure that, if you're going to do asymptotics with patients, let's say, then you need to make sure that the time horizon, the observation times are dense, for example, right? So there are conditions there, but you can allow them to be informative, and as long as their distributions depend on observables. Okay. For page 15, you mentioned MTJ for the distribution. What kind of distribution is it? Okay, so let me go to page 15. This is just generically its distribution given HJ. So under this model, this just represents the generic distribution. There's no structure being imposed in this lemma. It's just saying that is the distribution of the latent state given H. That's all.